chapter 8, the whole of chapter 8 basically is an introduction to mechanics. So you won't understand everything straight away. So the idea, once you've done the stuff from chapters 9 and chapters 10, then chapter 8 will seem more sensible because there's a whole load of language and ideas as well. So don't worry about chapter 8 too much. We'll get into it eventually. Okay. The first example in the book is about the motion of a basketball. Okay. I've got this image of a basketball and a basketball player. Okay, so as it leaves, the motion of a basketball as it leaves the player's hand and passes through the net can be modeled using the equation. Okay, so they're giving you a quadratic equation. H equals 2 plus 1.1x minus 0.1x squared. So this is used to model the motion of the basketball. H is the height of the ball above the ground. X is the horizontal distance traveled. Okay, so it's a negative quadratic, which is what the shape of the motion makes. It's a negative going like that, negative quadratic. So that seems to be like a sensible model. Okay, first part of the question. Okay, find the height of the basketball when it is released. So when the ball is released, that corresponds to this point being x equals 0. In other words, you need to substitute x is 0. So the initial height of the ball will just be 2 meters above the ground. Okay. Find the height of the ball at a horizontal distance of 0.5 meters. So this is telling you x is equal to 0.5. So you do the same thing. You put x equals 0.5 into the equation, and you just work out the value of h. 2 plus 1.1 times by 0.5 into a calculator. That gives you the height of 2.525 meters above the ground. Okay, so it could be over here somewhere to the right. Okay. Part B, use the model to predict the height of the ball when it has a horizontal distance of 15. Okay, so according to the model, the height predicted would be when x is 15. So you plug in 15 into the equation. So you just do 2 plus 1.1 times by 15 minus 0.1 times 15 squared. Okay, and that will give you a value of negative 4. So that tells you h equals minus 4. That's according to the model. Very weird answer. So they ask you to comment on the validity of this prediction. Obviously, according to the model, the ball will be 4 meters below the ground, which is not physically possible from the basketball games I've seen. So you give a reason. So you could say something like height h is greater than equal to 0. For all x, for all distances x. So minus 4, yeah, so the model is not valid for x equal to 15. So yeah, so since h equals minus 4, model is not valid. Model is not valid for x equal to 15. You get a silly answer. Next section, again, it's an introduction to some of the language that you'll see in the later chapters, and also in year 2. Okay, so you don't need to worry about memorizing anything. Once you do questions later on in chapter 9, 10, 11, you'll get used to all the language anyway. So this is just an introduction. So if you do physics, you'll come across some of this before. Okay, so first word, particle. Okay, so quite often you can model objects as particles. So quite often they model a person as a particle. Okay, so for example, if this is, so we're looking at the word particle. So definition of a particle, the mass of the object is concentrated at a single point. So you ignore the dimensions of the object. Dimensions of the object are negligible. So you don't worry about the height, the width of the object. You just assume that the mass of the object is concentrated at a single point. Okay. Also, any kind of air resistance is ignored. Okay, so it's a very simple way to model something. So quite often, if you have a person, okay, suppose you've got somebody who is 75 kilos in mass. So suppose that person is standing on the floor. Okay, so instead of drawing a person, you can model the person as a particle. Okay, so if somebody's standing on the floor and they have a mass of 75 kilos, do you know what their weight is? What is the weight of that person? How do you work out their weight? Yeah, so if you do if you take G to be 10, they do, but in maths they take G to be 9.8. Okay, so you'll do that later on anyway. So you could do something like this. Okay, so you'll do this later on, but the weight is 75 times G. Okay, but G is not grams. Okay, it's times 9.8. Okay, and the weight is in newtons. So the weight is a force. So you'll see this later on. N is for newtons. Okay, if somebody's standing on the floor, the person does not crash through the floor. There's another force acting upwards on the person. Do you know what that force is called? Reaction, yeah. So it's called the normal reaction. So again, you'll deal with this later on. So that force, they use the letter R for normal reaction. Okay, I'll just write it down. Okay. You'll see that later on. So particle mass is concentrated at a single point. Ignore dimensions, ignore air resistance. Okay. Okay. A rod is like a pole or a beam. Mass is concentrated on a line, rigid, so stiff. Okay. Laminar is basically like a flat, something which is flat. Laminar, you can ignore the area. So the area can be ignored. So the example would be like a sheet of paper. Another example would be like a DVD disc. For example, that can be modeled as a laminar. So you could ignore the thickness of it. Okay, uniform body. Okay, so on the bottom you've got these two sticks. So this on one on the left is like a baton. Okay, so this would be called a uniform body. Okay, because it looks very evenly constructed. So when you have a uniform body, the mass is distributed evenly, and the center of mass is in the middle. So the center of the mass is in the geometrical center. So in this case, this point here is the center of mass. Yeah. Okay. So the center of mass acts at the middle for a uniform body. Now, the diagram on the right, you can see it's kind of like a baseball. So this is an example of a non-uniform body. Non-uniform body. So the center of mass won't be in the middle. If you think about it, it'll be more to the left. That point will be the center of mass. Over here, slightly to the left. Okay. So those are the two ideas of uniform and non-uniform. Have you come across that before? Uniform and non-uniform? You'll see it later on. Okay. The next one, light object. So if an object is modeled as a light object, then basically you could ignore the mass. You can treat the mass as zero. So the mass is negligible. Inextensible string. Okay, so it means a string which cannot be stretched. Okay, on the right, okay, this thing here, this circle, called a pulley. Okay, you have a string passing through the pulley, and you've got two masses attached at the ends of the string. Normally, you would assume the string is inextensible, not stretchy. Okay, so if I release the pulley, what will happen to the masses? If I just release the pulley, if I release the masses, what will happen to the objects in that pulley? If I release the mass M1 and M2, what will happen? Can you describe the motion? One mass is 1 kilo, the other is 2 kilos. What will happen? And I release the masses. If I drop the masses, what will happen? The second one, pull down the string. Okay, so one will go down and the other will go up. So the heavier one will go down. Okay, so what will happen? Okay, so when you release the masses, this one will go down. So I'm going to use letter A for acceleration. So it's going to accelerate as some number, A equals meters per second squared is acceleration. But because these are connected, this mass will go up. This will accelerate upwards with the same acceleration. So accelerate. So this is one of the properties of an extensible string. The acceleration is the same in both objects connected by a taut inextensible string. That taut means there's tension in the string. Okay, so when the bodies are released, there's tension in the string, so we say the string is taut. So this body will go up by the same acceleration. Okay, so that's one of the properties of an inextensible string. So the tension is going to be the same, but you'll deal with that later on. Okay, so if you know anything about physics, that mass will be 2 times 9.8 newtons, and this mass will have 1 times 9.8 newtons. That's the force on the bodies. Again, if you know anything about physics, there'll be tension in the string. Okay, smooth pulley. Okay, you'll see later on in chapter 10 how to deal with this situation. Surface which is smooth. Okay, if you're going to model something as a smooth surface, you're talking about maybe something like a ice rink. Ice rink would be an example. You go ice skating, or maybe a frozen lake, for example. So, smooth surface, you can assume that there is no friction between the surface and the body. So you can assume there's no friction. So you can assume there's no force slowing down any kind of motion. Rough surface is not smooth, so that means there is friction involved. So on a rough surface, there will be a friction force which will slow down the motion. Okay, so on the diagram on the right, you have this cute diagram. So on the snow, that could be more. So on a snowy surface, you could model that as a smooth surface. That seems reasonable. So on the left, you can ignore the friction. This guy is sliding on the grass. So the grass, obviously the surface of the grass is going to slow down the motion. So there'll be friction involved. So you would model that surface as a rough surface. Okay, so there is some kind of friction, so the friction opposes the motion. Is that okay? Again, this is just an introduction to the language. When you do questions, you'll see it more often. Wire, thin metal, treated as one-dimensional, smooth and light pulley. Okay, so the pulley I've just mentioned. Okay, the bead. A bead is a particle with a hole in it for threading on a wire. So on my left, I've drawn a diagram. So basically, it's like a necklace. So a bead is like a single particle with a hole in it, and the bead moves freely along the string. Peg, a support on which, okay, peg is a weird thing. A support from which a body can be suspended or rested. Don't worry, you'll see it when we do the questions. Okay, air resistance is a good one. Air resistance, I mean, the example would be with the skydiver, parachutist. Okay, if you're falling through the air, obviously you've got gravity. So gravity is attracting the person towards the ground. So gravity acts downwards on the person. You've got the gravitational force on the person. Okay, but obviously you have the air resistance acting upwards. Okay, so quite often in questions, air resistance will be ignored. So they'll say in the question, air resistance can be ignored, just to make the model simpler. Okay, hopefully you've heard of gravity. Gravity is the force of attraction between all objects, and the acceleration due to gravity we take to be 9.8 meters per second squared. So if you drop something to the ground, it is accelerating with a velocity of 9.8. It is accelerating at 9.8 meters per second squared. That's if you drop anything towards the ground. Okay, so maybe in physics you do 9.81, but in mathematics they take g to be 9.8. So g is the acceleration due to gravity. So there's one example I can talk about. This is about a piece of string attached to a ceiling. Okay, try to draw a diagram. Okay, so this is the ceiling. Okay, you have a piece of string, there's a mass attached, and the mass is drawn to one side. Okay, so the idea is that, okay, this is the string being drawn to one side, this is the mass. Okay, so to drag the mass to one side, okay, that mass must have been pulled to one side. So you can imagine there's a pulling force. So a kind of pulling force. Okay. Okay, suppose this object has a mass m kilograms. Okay, that means the weight will be its mass times by g. Remember, in these situations, g is always taken to be 9.8 meters per second squared. But don't worry yet. If you do physics, you'll be familiar with this. The weight will be mg, mass times 9.8. Then that will be newtons. Okay, so this body is attached to a piece of string. Okay, so when you pull it to the side, there's going to be tension in the string. Okay, so the tension acts in this direction. So the tension in the string stops the body from being pulled further and further away. So we call that T tension. Okay. The tension is the force in the string. So you'll see these ideas later on. So the question is actually asking something much more simple than that. State the effect of the following assumptions. So if the string is light and inextensible, according to the table, you can ignore the mass of the string and you can ignore any stretching effect caused by the mass. Okay, so in reality, the mass will cause the string to stretch a little bit, but for the purpose of this model, if you assume it's inextensible, then you can ignore any stretching effect caused by the mass. And obviously, you can ignore the mass of the string because we say it's light string. If you assume the mass is modeled as a particle, so again, directly from the table, you can say you could ignore the dimensions of the particle. You could ignore the effects of air resistance. Ignore any kind of rotational effect caused by any of the forces. So basically, it's just the information in the table. Page 122 goes through the units they use in mechanics. So obviously, you've seen this somewhere before. Mass, okay, they're called SI units. So these are the standard units they use in physics. Mass, kilograms, length or displacement, meters, time in seconds. Okay, velocity is meters per second, ms minus 1, or you can write m dash m line s. Acceleration, meters per second per second, or simply meters per second squared. Weight or force, newtons. Okay, so kilograms meters per second is a bit unusual. Normally just newtons. So those are the units that they use. Okay, bit of a language introduction again. I've talked about this already a little bit. So if this is a book, okay, so in this one over here, you've got a book on a table. Okay, so the idea, I mean, you could model the book as a particle, but when the book is lying on the table, it's going to have some kind of weight. So that force is the weight. Okay, because the book does not crash through the table, that means the table must exert a force onto the book as well. That force is called the normal reaction. That force is called the normal reaction. So it's the force exerted on the book by the table. Okay? So you can see, in this case, R has to be equal to W if the book is just sitting there. So in this case, normal reaction is going to be equal to the weight. Nothing weird is happening. So the weight acts downwards. Okay, so again, I mention it now. If you want to work out the weight, you'll see it later on. The weight on an object is calculated as its mass in kilos multiplied by G, where G is 9.8. So in other words, it's M times 9.8. But you'll see this later on, and the units will be newtons. Okay, friction is the force which opposes the motion. So it's the force which opposes motion. Okay, so if the book is being pushed to the right, then the friction from the table will oppose the motion. So the frictional force always opposes any kind of motion. An object is being pulled by a string. Okay, so you've seen this before. Then the force in the string is called tension. So we have tension in the string. That's the pulling force in the string. If an object is being pushed along using a light rod, that's called a thrust. So the thrust is like a pushing force. That's called thrust. Okay. This example is about a boat. Okay, so obviously the boat is going to have some kind of weight. Okay, obviously the boat does not sink to the bottom, doesn't sink to the bottom because the water is exerting a force upwards. So that upward force is called the buoyancy. So the force from the water, which prevents the boat from sinking, is called the buoyancy. Okay, air resistance you've seen. So you've got the weight of the skydiver and you got the air resistance acting upwards. Okay, so that's an introduction to some of the ideas. Okay, it will make more sense when we do chapters 9 and 11, 9 and 10. That's just some of the ideas. Okay, this one is just calculation. She got to do it without me. SI units. So kilometers is not an SI unit. You need to convert it into meters. So 4 kilometers is 4,000 meters. So that's what it is in SI units. So you want the standard units they use. Grams is not an SI unit. You need to convert it into kilograms. To convert into kilograms, you just divide by 1,000. Okay. So now that weight, that mass is now in SI units, kilograms. Okay. This is a velocity in kilometers per hour, but that's not an SI unit. You need to convert it into meters per second to be in SI units. So you convert it into meters per hour first, times by 1,000, get meters per 1 hour. Then there are 3,600 seconds in 1 hour, so you divide by 3,600 to get the meters per second conversion. So now that is in SI units. Okay, so hopefully you knew how to do that before me. Okay, example 4, names of forces. Okay, so got this plane. So B is called forward thrust. So forward thrust is basically the force from the engine. So you get that from the engine of the plane. That's called the forward thrust. Obviously got the weight of the plane acting downwards. The plane is flying along. You have air resistance. I mean, they call it drag, really. I think the technical word is probably drag. So that is called drag or air resistance. And also, the force which keeps the plane up in the air is called lift. So also known as upward thrust. That's the force that keeps the plane upwards. Okay. That's my introduction.